want to do is discuss more generally how to think about nonlinear systems. So we're going to talk about the stability of nonlinear systems and to think about the stability of these equations. So when I look at an equation like this, I say I have an equilibrium here. Is it stable? And if it's stable, what kind of behavior does it represent? And if you remember, we had different ways of classifying these equilibria, depending on how the solutions around them behaved. Do you remember what they were? So an equilibrium can be, we have different kinds of names. It can be stable or unstable, and it can be of different kinds. So do you remember what kinds of equilibria we have? So let's review this. If you remember competition, in the competition process, we had two populations that in isolation, the one would go to level S and the one would go to level K. And we had a situation where the isoclines might look like that, and this would be the coexistence equilibrium. And in this case, we said if the coexistence equilibrium lies below the dotted line, connecting X and K and S, and that depended on our values alpha and beta that represented interspecific, the strength of interspecific competition compared to intraspecific competition, then we said solutions can be doing something that looks like this. Remember that for the competition model. What did we call that? What did we call that equilibrium in the competition model? We called it a stable. Sorry? Well, there were two kinds of things. There were nodes and spirals. Is that a spiral? No, it's a node. So that's a stable node. When solutions look like this, when we plot them, when the arrows go the other way, locally, they kind of move away from it, then we call it an unstable node. And so this would happen in the case where, if this were, sorry, in this case it would, I got it mixed up. In this case it would be an unstable node. In the case where this and this are S and K, and then this lay above these two, then that would be a stable node. But when this is the equilibrium and that is the isolation equilibrium, then it's an unstable node. But also in the competition equation, we saw that the origin, solutions would seem like they're going towards the origin and then move away. What did we call that? Yeah, we call that a saddle point. And then we also had the cases like this one, where the solutions would wind in or wind out. If they wind in, we called it a stable spiral, and if they wound out, we called it unstable spiral. And if they just formed circles, then we call it a center. So those are the different kinds of equilibria. Now, how can we find that out using analytical methods? Now, in one dimension, when we looked at the logistic equation, and remember when we said dx dt is a function of f of x. And for example, if we plot x versus f of x. Now, this is not a phase plane analysis. This is just plotting the function f as plotting f as a function of its argument x. Remember we said that the way to tell if these equilibria, this is where f of x equals 0, dx dt equals 0. The way to tell if these are stable or unstable is to do what? What did we need to do to tell if they were stable or unstable? The answer is in front of you. What do we need to do to tell if the equilibrium that corresponds to, that makes the f dx equal to 0, to decide whether that's a stable or unstable equilibrium, what do we need to do? Right, so we find the slope, which is taking the derivative of the function at the point. So if I take the derivative of this function, like if this function is ax 1 minus x upon s, if f of x is equal to this, then the derivative of the function df dx is equal to, the first term is ax, so it's just a, and the second term is ax squared upon s, so that would just be axs times 2. Okay? If I evaluate the f dx at x equals 0, which is the one equilibrium, then it's equal to a. This is not working, so let's try. If I evaluate the f dx at the other equilibrium, which is at x equal to s, that's the other equilibrium, then when x is equal to s, it's just a minus 2a, which is minus a. So in the logistic model, a is positive. So the slope here is a, and the slope here is minus a, which is not surprising because this is a symmetric function. So we're not surprised to find out that if the slope is a, the slope is minus a. This tells you right away that this equilibrium is unstable because the f dx at x equal to a is greater than 0, and this is stable because the f dx, sorry, at x equal to 0, at x equal to s is minus a, which is negative, which means it's stable. So this theorem applies. So let me make this a bit bigger. So you've got to look at the f dx at x equal to the equilibrium x hat. In the one case, the equilibrium x hat is 0. In the other case, it's s. And so you need to understand this theorem. And this is a theorem that we go way back towards the beginning of the course. And when we get to two-dimensional systems like this, let's just go up. Yeah. So here we have a two-dimensional model, and I've written it in terms of x1 and x2 rather than x and y. And it's just more convenient to do it like this, because this actually generalizes to 3, 4, 5, 6 equations. In this case, if I make this a little bigger, it may be easier to read. Okay, so there's our equation, which you can write in vector notation using f in its bold form to represent two functions, f1 and f2, and x to represent x1 and x2, and the equilibrium x hat is x1 hat, x2 hat. Now you can, I might come back to this, but what I'm going to do is I'm going to say these functions can be differentiated. So I'm going to use the notation, I'm going to take a function like, for example, f1 as a function of x1 and x2. That's the first equation in this model. And I'm going to take its partial derivative with respect to x2, just as an example. So f1 is a function of x1 and x2, and I can take its partial derivative with regard to x2. And then I can evaluate this at an equilibrium. And this equilibrium I call x1 hat and x2 hat. So this is what this notation means. This notation means you take the function f1 as a function of x1 and x2, you differentiate it, you take its partial derivative with respect to x2, and then you evaluate it at the equilibrium of interest, which in this case I'm just calling x1 hat and x2 hat. Does everybody understand how I've generalized from the one-dimensional model? In the one-dimensional model, I took the derivative, the f dx, and looked at it at x hat, and in this case x hat was equal to either 0 or s. And I calculated the value of the derivative. The value of the derivative at a particular point is a number. It's not a function. f1 is a function of two variables, x1 and x2. When I take its derivative, I still get a function of these variables, but now the function is different. So for example, f of x is a quadratic function, ax 1 minus x upon x. When I take its derivative with respect to x, I still get a function of x, but it's now linear. Because when you take a derivative of a polynomial, it goes down by one order of magnitude. And this is what you would expect, is that if x2 appears up to the power squared, then when I take its derivative with respect to x2, I'll get a function of x2 that is now linear instead of quadratic. Or if it's cubic, then once I take the derivative, I expect to get a quadratic, and so on. But there are two variables. I use this notation. This notation is meant to be shorthand for the fact that I've taken the derivative of f1 with respect to x2 and evaluated it at the points x1 and x2, and it gives me a number. Now what I can show is that if I take this equation, dx dt is a function of x, this is the vector form of this equation, and I say, okay, I'm now going to expand it around this equilibrium. This equilibrium is x hat. So then I define a new variable z, where z is the distance of, represents the distance of x1 at time t to x1 hat, and x2 at time t to x2 hat. So what I'm doing, and so I should probably draw this for you, is I'm saying that I have an equation, the x1 dt is f1 of x1, x2, and the x2 dt is another function f2 of x1 and x2. And let's say this is something like the Lotka-Volterra competition model or the Lotka-Volterra prey-predator model, whatever it is. Now I'm looking at a phase plane analysis. So this is x2 axis, this is x1. I draw the isoclines, and I get some kind of intersection over here. And this is what I'm calling x1 hat, x2 hat. Now what I'm interested in is that if I'm at a point near here, near the equilibrium, and I'll call this point x1 at t, x2 t, then there's a vertical distance and a horizontal distance of this point to this point. I'm calling this horizontal distance, I'm saying this is z1 and this is z2. In this case, z2 is negative. I mean, z2 is positive because I have to go down. And z1 is negative because it's smaller than this value. If it was on the other side, z1 would be positive because it's bigger. So it represents the distance of this point to this point, looking at the coordinates. When z1 and z2 go to 0, it means this point and this point coincide. So z1 and z2 represent the distance of this point from the equilibrium. So what I'm going to do is, instead of writing these equations, the x1 dt and the x2 dt, in terms of the variables x1 and x2, I'm going to write them in terms of z1 and z2. So I'm interested in how far the system is from this equilibrium. And I want to know, is z1 changing so that I'm getting closer to the equilibrium, or is it changing so I get further from the equilibrium? So in order to understand what z1 and z2 are doing close to this point, when this point is close to this point, what you do is you take a linear approximation of these functions. You expand them so you get the constant term and the linear term. And so you can see how to do that. Again, I'm not going to ask you how to do these things. This is just a way of background. You can read up here. It'll tell you how to do it. But when you take the expanded system, then you're expressing the z1 dt in terms of the derivative of f1 and x1 evaluated at the equilibrium times z1, and then the f1 dx2 evaluated at the equilibrium times z2, and then the z2 dt you can also linearize, and you can get this system of equations. Now this is a linear system because this is a number, this is a number, this is a number, this is a number. So it's like saying the z1 this is like saying the z1 dt is equal to a times z1 plus b times z2. The z2 dt is equal to c times z1 plus d times z2, where a is the partial derivative of f1 dx1 evaluated at x1 hat, x2 hat, and so on. So this is called the linearization of the nonlinear system around the equilibrium. And if you want to see how this is done for different models, I have a section here called optional material. And I developed this in terms of writing down the models like this. And the reason why I wrote down the models like this in terms of the per capita expressions, x1 times the per capita growth rate, x2, is that it then makes it a lot easier to actually do the expansion. And then I do this for things like the Lotka-Volterra model. Again, those of you who are a little overwhelmed, don't worry about this at all. Those of you who are interested, you can follow this material. The takeaway point that I want to make in terms of your understanding about stability theory is that in the same way that we can take the linear system dx dt equals f of x and evaluate the derivative of f at the equilibrium x and look at its sign in order to determine the stability properties of x. So for a two-dimensional system, we can take the partial derivatives of f with respect to x1 and x2, and the partial derivative of f1 and the partial derivative of f2 with respect to their two variables, so that we get four partial derivatives. These are the four partial derivatives. These partial derivatives are a way of saying that in a neighborhood of this equilibrium, this point behaves like this system will predict, like a linearized system will predict. And the closer this point is to the equilibrium, the better this linearized approximation is. So what that says is that the stability properties of this nonlinear system in the neighborhood of the equilibrium around which we generate these partial derivatives will give us a linear system, and the stability properties of this linear system will tell us what the stability properties of this equilibrium are. So it'll tell us if solutions are attracted to it or if solutions move away from it. Now, in linear systems, we saw that solutions can either be attracted, in which case we call them stable nodes, or they can be repulsed in all directions, unstable nodes, or they can wind around and move in which case they're stable spirals, or they can wind out, in which case they're unstable spirals, or solutions can appear to be attracted in one direction and move off in other directions. So they move off in this direction and they attracted in this direction. So in this direction, so they seem to be coming in, but then they move away. And they come in this direction and they move off in that direction, or they move down in that direction. Then it's called an unstable saddle. And it's called unstable rather than stable because ultimately the solution moves away from the point. So if you wait long enough, the solution moves away. It may seem initially to be moving in, depending where you start. If you start over here, it immediately moves away. If you start over here, it seems to move in and then move away. So those are the possibilities. Any questions? So how do we know which one of these solutions applies? Well, it's got to do with this linear system. This linear system can be written in this form. I can write it as dz dt, where z is now a boldface, and it's z1 and z2, so it's a vector. And I can write this as a matrix A times z, where A is the matrix A, B, C, D. Now, if you remember, if I have a linear system and I look at the solution to the linear system, do you remember what the solution to a linear system looks like? So we looked at the theory of solutions to linear systems. In one dimension, dx dt equals ax. What is the solution to that equation? If I start out at x times 0 equals x0. What is the solution to this equation? X of t equals x0 e to the at. If a is negative, it's stable. If a is positive, I'm moving away from the equilibrium. The equilibrium in this case is x equals 0. X hat equals 0 is the only equilibrium. The only thing that makes the right-hand side 0 is x equal to 0. Unless a is equal to 0. If a is equal to 0, then I don't even have a model, so we don't bother with that. Now, in two dimensions, you remember how to write down the solution to this equation. How do you write down the solution? Let's see. Z1 of t is equal to, and Z2 of t is equal to. Do you remember what the solution is? So the solution is a linear combination of two exponential functions. Remember that. So in one dimension, it's one exponential function. In two dimensions, it's two exponential functions. What are the exponents? Yeah? Yeah, so if you look at the eigenvalues of this matrix A, you get two eigenvalues, lambda 1 and lambda 2. So in two dimensions, the solution is going to be e to the lambda 1 and e to the lambda 2 times t. And now they're going to be constants. Let's say alpha, beta, gamma, delta. You remember how I find the value of the constants alpha and beta and gamma and delta?